Hello, everyone. In this lesson, I would like to talk about the number e expressed as a limit and an application of it. In order for us to understand e better, we know that e is a constant. It equals to 2.7 and followed by many digits. Okay, 2.7 and followed by many digits afterwards. You can look it up online. I'm sure you can find the, more digits about E. But here, what we want to use is that we have just learned about the derivative of natural logarithm. Okay, so let me write it down. Okay, so you know what I'm talking about. So f of x equals to ln x. We understand that this function, its domain is x is greater than 0. X is greater than 0. Once we know its derivative, right? We know the derivative. Of course, we know the formula. So the derivative of f of x is equal to 1 over x. And of course, the domain is still x is greater than 0, right? The domain of the derivative is not going to be outside the domain of the function. So this domain still applies, okay, for the derivative. But from here, if we do a simple substitution, right, if we choose x equals to 1, and what we'll get is that we found that when x is equals to 1, the derivative at this point is equals to 1 as well. Okay, so we're going to make some use of it and derive something that eventually leads to e is represented as a limit. So here it comes, right? So we got f of the derivative of 1 is equal to the derivative of ln x at 1 is equal to 1. According to the limit, the definition of limit, okay, a definition of limit. The definition of limit is when h is approaching 0, right? And this is the derivative of the function f at 1. So by definition of limit is f of 1 plus h subtracting the function's value at 1, which is over h. And from the function, we can tell what f of 1 over h is, what is f of 1 plus h and f of 1. So let's see what their values are, right? We know f of x equals to ln x, right? So we just gonna put it in here. So f of 1, we're gonna replace x by 1, of course. ln 1 is equal to 0. ln 1 plus h. Of course, x is replaced by 1 plus h. So at this point, if we substitute in this limit setting by the function, which is f of 1 plus h, right? And that's ln 1 plus h. That's ln 1 plus h. F of 1, that's 0. That's 0. And of course, we can omit it. So next step, we're going to do it just a little bit cleanup. And what is more, we're going to write this slightly differently, but algebraically still the same, which is, okay, we're going to multiply this h, or divide by h. We're going to write it as 1 multiplied by 1 over h. Okay, that doesn't change the nature of the function. Okay, so now we are going to apply some logarithm properties. Okay, what's logarithm properties? Okay, so let me write down the logarithm properties, right? The first important property of logarithm, of course, we know is the product rule. A times B, product. Okay, that equals to ln A plus ln B. The second important property is ln quotient rule. So ln of capital A divided by capital B, and that equals to ln A subtract ln B. The third one, which is the one we are going to use, is logarithm, and we have a capital A here, but there's a little power. The power of it is, say, we're going to use heart, okay? And this power can be brought down in front of logarithm. So we have these three properties. I'm going to box them, okay? I just hope that we've seen this often enough. Sorry. I'm going to box them, all right? So let's box them. Quotient rule. We don't have addition rule nor subtraction rule. So these are the three major rules of logarithms. So once we get to this point, we are going to apply the power rule, which is the third one, right? So we're going to see, but we're going to apply the power rule from right to left, which we're going to treat 1/8 as the heart, which is right in front of ln. We're going to bring it up to be the power inside the logarithm. Okay, so I'm going to show you next. All right. So applying the power rule, so I'm going to copy this power so you can do a comparison, right? And we're going to do it from right to left. We're going to treat 1/8 as the power and brought it inside the logarithm. So that's our next step. Okay, that's our next step. And what do we use? What do we do this for? Right? Because ultimately we have to go to the representation of E, right? In the representation of E, we're going to see how can it represent E in relationship with this limit. Before we do that, let's summarize what we have done. What we have done here, we have demonstrated that this limit is equals to 1. Okay, so we're going to summarize it. That is, this limit is equals to 1. All right? Okay. And next, we basically got another representation of 1, right? Because this limit is proven to be equals to 1. So we know that E is equal to E to the power of 1, of course, right? That is true with any number. And then what we're going to do next is that we're going to replace this 1 by its equal. So 1 equals to this gigantic limit. Then you say, why do we want to do that? Why do we make things more complicated? Well, keep on watching, and then derive on your own, okay? Derive along my sides. As you can see, we got this limit, right? But we have learned another property back in the section of limit. What it says, okay, I'm going to bring you the flashcards. Okay, the flashcards about that. At the time we talk about it, it's very important results. And now we're going to use it again. Okay. So there we go. I'm going to find it. Okay, just give me a second. This is about that limit is brought in and out through a function. Let's see. Okay, continuity. There we go. We're getting closer. We are getting closer and closer yet. So this is going to be the one. Yes, this is the one I'm looking for. This is the one I'm looking for. What this theorem says, f is continuous. Okay, well, e to the power x is a continuous function everywhere. Okay, so I'm gonna maybe copy this piece, okay, and bring it to our screen. Bring it to our screen. Okay, so we can use a larger screen. Okay. So with this property, how do we use this property? Obviously, in this theorem, the property is going to be applied to E. So E is F. Okay, E is F. The limit was inside. So now we want to bring the limit outside. You can see this theorem, you can do it from left to right or right to left, right? So we're going to do it from right to left, which is bring the limit outside. So what we're going to do is that we're going to take this limit, okay, outside. And now we got e raised to the power of ln. We got this power for e. Okay, so we use this theorem because e to the power x is a continuous function. Not only it is continuous, it is also differentiable. But what we only need is, continuity here to apply this theorem. So by the time we get here, and something interesting is going to happen because there's another property. There's another property about E we're going to use. Okay, there's another property about E we're going to use. What is the other property, right? That property comes from here, okay? By definition of logarithm, say if we say logarithm of, bologna equals to, I'm going to use the triangle, okay? This is a placeholder, okay? By definition, it implies, right? Left implies right, and the right side is e raised to the power of triangle is going to equal to omega, okay? So that's the relationship they're in. That's the definition of logarithm. Okay, so we got this. Now from here, what if we take this piece? Right? I'm going to take this piece right next to it. Okay. The triangle is also represented as a ln omega. So if I replace triangle by its equal, I would place ln omega equals to b power e equals to omega. So this is another identity that you probably have learned before if you have forgotten, but now we're just deriving it. We're just re-deriving it. So that's the other property we're going to use. Okay, so I'm going to box it. All right, so I'm going to take this box, the results, and we're going to apply over here. How are we going to apply it? We're going to apply it to inside the limit. Okay, so you can see we have an E here. we have E. And the ln, we have ln, right? We have e to the power ln, e to the power ln. So what is omega? Omega is the whole of that, right? And this property tells us it is just equal to omega, okay? So the whole of it, oh, actually, I don't need to, okay, yeah, we're good. Okay, so I'm going to apply this property to E. Our omega is this piece. So I'm going to bring that down. Okay, so this is the E. I want you to see clearly that this is E, ln, omega is that piece. Okay, so we're gonna bring omega in there. So this piece is omega as well. Okay, so we are applying this property over here, and of course our omega is the one we just deleted. Same thing. All right, so we get to review some of our logarithm properties and review our theorems, and that's what happened. So now what do we get? If you look at the leftmost side of this string of equal sign, and if you see the rightmost side of it, what we have found, we found that E is equal to a limit. And this limit is an interesting one. Okay, this limit is an interesting one. There are a couple of different versions by some simple substitution. For example, as h approaching 0, the h approaching 0, 1 over h. 1 over h. Okay, now what if I change h to be 0? No problem, to be x, right? No problem. It's just a simple substitution. So you would see many different versions of this. Sometimes h is replacing, x is replacing h. So that's one version. That's another version. Okay, they all mean the same thing, really. They really all mean the same thing. And another version of this is replacing x by n. And n as a subsequence of x, which is approaching 0, also works, right? So we'll replace x by 1 over n. Okay, so this is the assumption. Okay, so still the same thing. We're going to let x to be 1 over n, and n approaches infinity. N approaches infinity. Okay, so in that case, 1 over n can replace x. Okay, 1 over n can replace x. So in this version, when x is approaching 0, n is approaching infinity. So we're going to substitute everything by n. So n is going to be approaching infinity. X will be replaced by 1 over n. And 1 over x. 1 over x is going to be equals to what? 1 over x is going to equals to n. So 1 over x will be replaced by n. So these are the different versions. These two versions are used the most often. Okay, we will talk about its application. So this is how we derived E as a limit, as an limit. Okay, E is being derived as a limit. So finally, okay, I found in the textbook that E gave us more digits, right? So I'm going to put it in here to conclude this clip. And it is equals to 2 point, okay, approximately equals to approximately. Let me find that approximating sign. There has to be somewhere. Wait. Approximation is not here. They're all not equal. Let's look at this piece. Here we go. I found it. Okay, approximately equal to 2.7182818. And we are given like 7 digits after decimal point. Okay, so if you remove this, that would be approximation. But a lot of people, like in most of the cases, we just use 2.7. We just use 2.7 and not using this value at all, just treat it as a constant. Okay, so that's all for this clip as how we derive E as a limit, And then the next question is, what is the use of it? We make it more complicated. Well, yes, it has some uses. So we're going to talk about it in another clip. Thank you for watching.